Hello students, Dr. Chatfield here. I want to tell you today about a physical chemistry experiment you'll be doing or analyzing in the lab, and that is the absorption spectrum of iodine vapor. So to talk about this, let's go to a PowerPoint. So this video is the second of two on this particular experiment. The first is on the process of doing the experiment, sample preparation, and the running of the spectrum, taking of the spectrum itself on the spectrometer. This is on the theory and the calculations that you'll do once you have the spectrum. So the purpose of this experiment is to determine the constants of an excited state, which is described by this term symbol here, from the spectrum of I2. And there are three things that you will determine from your experiment: T prime, omega E prime, and omega E X prime. These are the minimum energy of the excited state, the vibrational frequency or vibrational constant of the excited state, and the anharmonicity constant for the excited state. So let's talk about the experiment and then how you'll determine these things. I won't say much about that experiment because that will be covered in the procedure for carrying out the experiment, because that will be covered in another video. But just briefly, you've got the picture of the spectrometer. And so you've got a light source. The beam will be collimated, then split, and one beam will go through your sample, the other beam will go through a reference cell, and then the results onto the detector. Sample preparation is covered in the other video. Ultimately, you will get a spectrum that looks like this, and this is what you will have to interpret, these peaks. So let's talk a little bit about the underlying theory then. In spectroscopy, of course, what you have is a sample that is initially in some energy level, and with light, you can excite the sample from one energy level to another. And the light will have some frequency nu. That's, of course, what we measure directly. So this slide talks about the quantum numbers that characterize the lower level and the quantum numbers that characterize the upper level. And so I want to talk about those, what characterizes the energy levels. So broadly, the total energy of a sample can be split into four components, approximately: translation, which is for linear motion, rotation, vibration, and the electronic energy itself. So the translational, rotational, and vibrational and electronic energies, each of those have levels. And so you can talk about the typical spacing between translational levels or between rotational levels or vibrational electronic. And what we find is that the spacing of translational levels is much smaller than rotational levels. In fact, the translational ones are practically a continuum. And then vibrational are spaced more widely apart and electronic most widely apart. In this particular experiment, we will not resolve translational or rotational levels, but we will resolve both vibrational and electronic. So what we have here is a diagram that will make fairly clear what is going on in our experiment. So remember, you're going to have I2, so it's a homonuclear diatomic molecule, and you can imagine one molecule at any point in time. There's going to be some internuclear bond distance. Now, the curves, you see here two curves. Those represent the potential energy surface in two different states. So that would be for the lower electronic state, the ground state, and this would be for the potential energy surface for an excited electronic state. And each of those states can have a set of vibrational levels, and you see those with the horizontal lines. You'll also see that for the ground electronic state, this distance right here represents R naught when we are in the ground electronic state. This distance here represents R naught when we're in the excited electronic state. So you'll notice, in fact, that R prime is not as bigger than R double prime naught. That's partly, largely because molecule is less tightly bound in the upper when it's in the excited electronic state. Okay. You'll also notice that the vibrational levels are a little more closely spaced in the upper state than in the lower state. That's because the vibrational frequency or the vibrational constant is going to be smaller in the upper state than in the lower state. So we can characterize the energy in the lower state. We'll use double prime to indicate the ground or a lower electronic state, and a single prime to indicate the excited electronic state. So the energy here is really being given in units of reciprocal centimeters, wave number units. So we've got a harmonic term right here and an anharmonic right term right here. And V double prime is the vibrational quantum number for the lower state. Okay. Then we have the likewise for the upper electronic state, but we have an extra term in our expression, and that's the T prime right here. T prime now is the difference between the minimum energy in the upper state and the minimum energy in the lower electronic state. So we're using T a little differently than we did in the HCl laboratory, where we there was the term, right? But here it's this energy difference. Okay. So ultimately there will be a transition as you go from the lower state to the upper state, and that's represented by this black arrow pointing up. That represents this transition. So this will be a transition if we just specify the vibrational quantum numbers from V double prime to V prime. That would be for the absorption of radiation. The convention, by the way, is to put the higher energy state on the left and the lower energy state on the right. If we were for emission, just for frame of reference, we would start in the upper state and emit and then go to the lower state. So that arrow will point to the right. But we're talking about absorption. Okay. Now we need to talk about a few more things. First of all these symbols, symbols here. This symbol is called a term symbol. Well, later in the lecture course, we'll talk about what all the components of this term symbol are, what they mean. But you have seen them before in the potential energy surface of a diatomic lab when you consulted the NIST website and you saw all these different electronic states. So that's the term symbol for the ground excited electronic state. This is the term symbol for the ground electronic state. And these over here, this is are two different term symbols for different electronic states of the atoms. So when R gets very large, and this X coordinate is R, you essentially break the bond and you have two individual atoms. So these are term symbols for the atoms. Okay. Let me erase those because it gets busy. Okay. So a little more background. I want to talk about two concepts called a vertical transition and the Frank-Condon factor. So the vertical transition is this idea that when the molecule absorbs a photon, the electrons change their organization around the nuclei. We say the electronic state changes, and that is essentially instantaneous because electrons move so much more quickly than the nuclei. So the internuclear distance r does not change during this electronic transition, and that's why the arrow is drawn vertically. We call it a vertical transition. This is related to the Born-Oppenheimer approximation, that the nuclei are essentially stationary, that the electrons travel much more quickly than the nuclei. A related concept is the Frank-Condon principle or Frank-Condon factor, and that is this. If we begin initially in the ground electronic state and in the lowest vibrational state within the ground electronic state, I'm going to draw the wave function for the ground vibrational state. It's, of course, a single peak there. And if you think of this as a probability density, in fact, the maximum is right in the middle. And so that means that most of the time, the most likely excitation will be when the molecule has this internuclear distance. So the transition would vertically right up to here. And it turns out that the most probable transition will be to this vibrational state. Okay. So that principle, that in the vertical transition, you go from this vibrational state in the lower electronic state to this pretty large V prime in the upper state is called the Frank-Condon principle, or we'll also speak of Frank-Condon factors. So that's the most likely transition. You can think of this classically this way. This distance in the upper state would be a classical turning point. So your molecule would momentarily come to stop vibrating, and then it would be stretching, stop, and then it would compress. And so it will spend a lot of time at that internuclear distance. So you excite preferentially to this pretty large V prime. This looks like it's about 30. I'm not counting, but it's pretty large. You can do other excitations, for example, up to a slightly smaller V prime or a slightly larger V prime, but the probability will be a little smaller, and therefore the peaks in your spectrum will be a little smaller. Okay, so we've seen most of what we need to see. The delta E then is given by the difference between this and this, and when you take that difference, you get this expression right here. And we want to relate this expression to the peaks in our spectrum, taking into account the concept of a vertical transition and the Frank-Condon factor. So this slide will make clear how you would do calculations based on the analysis of your spectrum. So a couple of things. Remember, double prime refers to the lower state, the ground electronic state, and you will look up in the NIST data the omega double prime, that's the vibrational constant for the lower state, and also the n-harmonicity constant. You'll look those up in the NIST website. You could, in principle, measure those. You could measure them with the same kind of experiment you did for HCl. That was an infrared experiment, and that will tell you that's infrared light does not have enough energy to excite from one electronic state to another electronic state in general, but it does have enough energy to excite within the ground electronic state to different vibrational levels. And so from the IR spectroscopy, you could measure omega E double prime and the n-harmonicity constant omega E XE double prime. But we're going to take those as given. We're not measuring them in this experiment. Also, all the peaks in the experiment that you're going to talk about will be for D bubble, analyzed will be for V double prime equals 0. So everything within these square brackets are known, okay, from the spectrum or from the NIST website. So those are givens. Now, what about the left-hand side? When you analyze your spectrum from the peaks, you will determine what, for a given peak, what the value of V prime is. And we'll talk about how to do that analysis in a moment. So these are things that are known. So what is it that you're going to determine from the spectrum? You're going to determine T prime, omega prime, the vibrational constant, and the anharmonicity constant for the upper state. It's really cool that you can characterize the upper electronic state so well. How will you do that? You'll do that by doing a polynomial fit. Okay, it will be a second order fit. So you can use, you can do a trend line, a polynomial trend line of second order within Excel. Because you'll have something like 10 or 15 peaks that you can identify in your spectrum, you'll effectively have 10 or 15 different equations like this, 10 or 15 data points. And so that will be plenty to do a fit where you're extracting 1, 2, 3 constants from your fit. So what is this A naught going to be equal? It's, notice the constant of the equation. So the A naught will be the sum of your T prime and everything that's in brackets right here. So those two things together give you A naught. And since what's over here in red is known, by difference you can figure out the T prime. Okay. I guess I should tell you what X is. X is going to be V prime plus a half. So X is known for your equation, you'll plug it in. This is V prime plus a half squared, so that's the X squared term right here. So then the coefficient of your first order term is just your omega prime, and your coefficient A2 of the other term is negative omega E x E prime. Okay, so from the fit, you're going to get all your constants, and that's what you needed. Okay, so the last thing we need to discuss is how you label the V primes in your data point in your from the spectrum that you take. So let's talk about that next. Okay, so here's a spectrum. The right kind of tells you what you need to know, but notice the wavelength goes from 500 on the left to 650 on the right. Small wavelength corresponds to high frequency or high energy difference, delta E. So we have three ranges here, by the way. This range is for transitions out of V double prime equals 0. So that's the ground vibrational level within the ground electronic state. And that's really all you're going to analyze. But there is some overlapping, and these slightly lower energy transitions are out of the V double prime equals 1 vibrational level. And then we even get the V double prime equal 2 at yet longer wavelength. So there will be overlapping peaks, and that will make it a little harder to analyze the spectrum. So let's look more closely at the peaks. Just want to give you some hints here. Okay. These peaks over in this region right here are only related to V double prime equals 0. So you can label them pretty easily. But there's one problem, and that is they get pretty small down here to the left, and you really can't tell which the first state is. The very first peak would be the 0, 0 peak, okay? From V double prime equals 0 up to V prime equals 0, but you can't see it. So therefore you can't really, once you find the first one, then you can just count up and you get all the others. Therefore, we're going to give you a guideline, and it's in your manual. It tells you what the frequency is for this peak, 0 to 23, or you also are told when this one is 0 to 24. So with those two numbers, you'll be able to label all of these peaks by the value of V prime, okay, right there. So you'll label them all. Now, in this region right here, it gets to be a little tricky because these peaks are double peaks. What's going on? Let me pick this one, for example. It's a double peak. The larger peak is for some excitation out of V double prime equals 0. The smaller peak is for excitation out of V double prime equals 1. And that's not the one you want. So you could pretty confidently say, okay, I know what this larger peak is. It's one that I care about. It corresponds to something out of V double prime equals 0. I'll just keep labeling the peaks marching along. And you can label several more pretty confidently, probably. Now notice right here, the double peaks, both are getting to be pretty equal. And over here, in fact, the first peak is pretty small and the second peak is pretty large. That's where it's going to get a little dangerous. You can maybe still use this one, but be aware it's now the smaller peak that corresponds to V double prime equals 0. So only go as far in your labeling as you're still confident that you can assign the proper peak here. Okay. Also, as you go along, these get also more inaccurate because the two peaks sort of shift each other inward. So the precise frequency that you need is not going to be quite so accurate. So, but you can label out to maybe this far or something. So I think this is all that you need. Let me just double check with the next slide. Yeah, so in your lab report, all of this is described, what I just told you about, all of the equations you need and so forth. What you'll need to do is determine the experimental values for these three things. Remember that you'll use the NIST data for the ground state vibrational frequency and the ground state and harmonicity constant. And you'll need those data. And you will then compare with your results with the NIST data for the excited electronic state. All these things are there, and that will be important for your report. So you can report your accuracy with respect to this other tabulated data. This tabulated data is fairly old, maybe from 1975 or so. They haven't updated it. There's more data in the literature, but it's not in the NIST website. So it could be that your results are even more accurate than the NIST. We don't know, but make the comparison. So that's it. So good luck with the experiment, and that's all for today.